Hello and welcome. In this video, we're going to take a look at some linear equations and what happens when we have multiple linear equations put together. We call that a system of linear equations, and depending on how many variables are involved, we may have different kinds of solutions, and we might try to sort of visualize those. So let's start off with two linear equations in two variables x and y. We've got two examples here. L1 I've just denoted because it's a line, ax plus by equals h, and I've got a second line, L2, and that would be cx plus dy equals k. Now, just so you know, we could rearrange these so that both of them are sort of a y equals mx plus b form, but this is a very just general standard form of a linear equation, a linear equation in two variables. And so a, b, c, d, h, and k are all just constants. They're all real numbers. And we've seen some examples of what this might look like when we have two lines on the same graph. For instance, if you're looking for like a break-even point, then we might try to graph a revenue function and a cost function and see where they cross each other. Or we might be looking for an equilibrium point in supply and demand, and we can start off with a linear supply curve and a linear demand curve and try to find the break-even point. So it's pretty similar. And in those examples, we're used to seeing L1 as being a line, either increasing or decreasing. And then we'll have L2 on there, and maybe that would be decreasing, let's say. And then whether it's a break-even point, or whether it's an equilibrium point, or whether it's just an intersection point, you can see that there's only one intersection point. And when we're trying to solve for the intersection point, we need to know what the coordinates are for both x and for y. So this is just an example. In this case, we would have a single solution, one intersection point. Now, it is theoretically possible to have two lines that are parallel to each other, in which case we may have some other situations instead of one solution. For instance, we could have L1 be, let's say, a decreasing line. And it is quite possible that L2, even if it's a different equation, is still an equation defining the same line. And so L1 and L2, even though they have different equations, still have all of the same points on their graphs. And so every single point along this line would be a solution to both functions. So there's infinitely many solutions in this case. Now, there is one other theoretical option, and that is to have the two lines be parallel but non-intersecting. And so we would have L1, and we can have L2, and here you can see that they're a parallel. So no matter where we try to travel, left or right, they're never going to intersect each other. There is no intersection point. There's no break-even point, no equilibrium point, none of that. This is a situation where we have no solution. Now this is a system of linear equations in two variables, but we can extend the same concept to having more than two variables. It gets a little bit tougher to visualize, but we can take a look at sort of a three-variable problem in a three-dimensional type of graph. Okay, suppose that I wanted to introduce three variables. Maybe I'll have an x, a y, and a z this case, and so I'll have coefficients a, b, and c, and then some constant d on the other side of the equation. This is still linear because each individual term is a degree of 1. There is no x squareds or y cubes or square roots of z, nothing else with other kinds of powers or trigonometric functions, exponentials, or logarithms. So let's then go ahead and make another linear equation and call it L2. And at this point in time, we're going to start running out of letters in the alphabet. So it might be better to take A, B, C, and D and reuse those letters, but we'll just give these ones little subscripts. A1, B1, C1, and D1 corresponding to line 1. And then we can come up with another line using A2, B2, C2, and D2. Using the same naming scheme, we can get a third line. Now, it gets a little bit trickier to try to graph these. These graphs actually would exist in 3 dimensions, and we would need 3 axes. Now, this isn't exactly a course in 3-dimensional graphing, but you might be able to try to visualize these. Sort of taking an extension of a line and extending that into a third dimension, it now becomes a plane. Just think of it like a piece of paper. And each of these linear equations is no longer a line, but a flat sheet of paper that extends infinitely in 3 dimensions. Let's see what kind of solutions we could get now. Okay, now you'll have to bear with me a little bit here because I'm trying to draw this on a flat screen, but in 3 dimensions. So you can try to imagine that L1 here is a piece of paper. And now we're going to take L2 and we're going to make that another piece of paper in some other orientation, and you might see them intersect each other. Okay, it's a little bit crude, but here you can see that I've got 2 pieces of paper intersecting each other, and there is actually this line that forms where the 2 pieces of paper would intersect each other so far. But we still have one more linear function to add, so just imagine a 3rd piece of paper gets added to the mix here. Okay, well, with a little bit of camera magic and a bit of shading here, now you can start to maybe get a picture. We've got 3 pieces of paper, all kind of coinciding with each other at a single point here. And so, much like in the example of 2 lines, we could have 3 planes intersecting at a single point, and this would end up being one solution. Now, can you think of a way that we could maybe have 3 planes, 3 pieces of paper like this, intersecting all along a common axis, all along a common line? Give it a try. See if you can visualize that. Okay, maybe you can try to imagine something like this scenario. I've got those 3 planes, the 3 pieces of paper, and you can see they are all intersecting along a common axis. And every single point along this line would be a point that is in each of the 3 planes. So here we can still get infinite solutions. Now, what might be actually the most easy to visualize is to try to imagine having 3 sheets of paper, 3 different planes here that don't intersect all in the same spot. They may intersect each other, but they don't all intersect in the exact same spot. And see if you can try to imagine that. Okay, and here I've got one more example where the blue and green intersect each other. Blue and red lines or planes intersect each other. And it's actually conceivable that the green and red planes may intersect each other if you extended them out far enough. But they're definitely not going to all intersect in one consistent spot, and so this would be corresponding to no solution. Now, if you wanted to, you can continue to extend this to more variables, but it's already getting pretty hard to try to imagine things in 3 dimensions, and the human brain, we cannot comprehend graphs in 4 or higher dimensions. But we can still apply the same idea. We can get one solution, infinite solutions, or no solutions. And a linear equation in n variables might be better off written out in terms of just one variable with some subscripts instead of having to choose x, y, and z, especially since it seems like we're running out at the end of the alphabet here. We can just use the same variable, x, all the time and use subscripts. So in general, if we want a linear equation in n variables, here's how we can write that. In order to make sure that we don't run out of different letters for each coefficient and each variable, we can just denote every coefficient as a, but then just use subscripts as we go through each of them. So a1 would be the first coefficient and a2 would be the second coefficient. And rather than using a different letter, x, y, z, and continuing on through an alphabet of different variables, we can just call every variable x with a different subscript, x1, x2, x3, and so on. And so we end up with a general linear equation that looks something like this. On the other side of the equation, we're going to need a constant. So let's make sure that that's a different letter than all of the coefficients. Let's call that b. So in this case, all of the a's, or let's say a sub i's, where I can be any number from 1 up to n, these are going to be coefficients. To make this a linear equation, at least one of those coefficients has to be non-zero. If they were all equal to 0, then we would have a pretty boring equation. And then b is just some constant. Now, of course, if you start having more than one linear equation with lots of variables like this, then we're going to have even more subscripts, and we may have to have another subscript for equation 1, equation 2, equation 3. So here's an example if I wanted to show you a system of linear equations in, let's say, 4 variables and 3 equations. All right, well, this might look like quite a bit of a mess here, but you can see the red equation, all of the coefficients have a 1, and the constant has a 1, and then we're just incrementing for each new variable. So we start with a11, a12, a13, and a14, and those would be all of the coefficients in the same equation, but corresponding to x1, x2, x3, x4. And then we have a constant on the right-hand side, and that constant is simply b1 because this is our first linear equation. In the next row down here, this equation, everything is going to have a subscript 2 because it's our second equation. a21, a22, a23, a24, and b2. And then our third equation will all have 3's in there. Now don't fret, because eventually we're going to compress this notation down into what we look at as a matrix. And that is going to be a much more convenient form than having to look at massive equations like this. I'll leave that for a future video and kind of end that here so that you get an idea at least of the different types of solutions that you can get when you have multiple linear equations in a system. And we'll look at one way that you can solve a system of equations in our next video. And once we know how to solve a system of equations using a little bit of algebra, then we can start taking this notation away, stripping it down to the parts that we need, and making it a lot more efficient. So I'll see you in the next video. Thanks for watching.